Welcome everyone to this SimSold accelerating design and analysis of facades. It is scheduled for an hour or so, but depending on the timing, the questions, it could be anything between 30 minutes to an hour. So hopefully we'll see how it goes. But then again, thank you very much for joining us. I hope you get something out from this webinar and you find it useful. So basically, my colleague here, Mo from SOTECH, will be joining and going through his experience with SimSolid. So before we join, I just thought we'd just start with a brief intros about myself and Mo. So I've been with Symmetry for over 15 years. I have a background in computer-aided engineering. I have been exposed to various simulation softwares across going from STAAD to ANSYS and Nastran. And now with this SimSolid software, I'm a professional member of the Institute of Mechanical Engineers, and I have been working with customers like yourselves across the UK, Ireland, and the Nordics. Now, Mo, if you want to say something.
Yeah. So hello everyone. Like Wasim said, my name is Mohammed. You can call me Mo for short. I'm a principal technical engineer at SOTECH. I've joined SOTECH in 2015 as a KTP associate, so that stands for Knowledge Transfer Partnership. Mechanical engineer by trade, so I've got a master's in mechanical engineering, but when I joined SOTECH, I've also done another master's in project management. So yeah, I've been with SOTECH for almost 8 years. Before that, I was in other industries, so automotive, oil and gas, and within all those industries, I've always used either CAD or some sort of design software, from Inventor, SolidWorks, anything in between. And in terms of analysis software or simulation, I've used heavily before ANSYS, Nastran, before I was introduced to SimSolid in 2017. So I've been using SimSolid for quite some time now, and it's obviously it's an honor to be here. And thank you very much, Team Symmetry, for the invite. So, like I said, an engineer from SOTECH, and I tend to, look after clients from our, any kind of location that we work, UK, Ireland or Europe or Middle East, anywhere I get involved. So basically, if there's any questions about, engineering of something, I get involved. It doesn't matter who it is, where it is. I'm the one really look after that department altogether.
Okay, thank you very much, Mo. So we're basically going to switch our cameras off just so that you have a better experience with the sharing the screens. So let's just go briefly through the agenda. Okay, so just a brief agenda to get you an idea of what is happening for the next 30-40 minutes. We've done the introductions. We're going to go through a little bit about Symmetry and ALTAIR. ALTAIR is the manufacturer of the SimSolid software. And then we're going to go through SimSolid, what is SimSolid, and then I'm going to just go through some sort of generic presentations around SimSolid, just to give you an idea of what its capabilities are and how it works, and then we'll go to Mo and share his experience about how they have sort of managed to use it within their industry, and then we'll go through a series of questions towards the end of the session. Okay, just a little bit about Symmetry. So I recognize some of the names already. Customers, for those who are not customers, Symmetry are a global Autodesk Platinum partner with offices in UK, Ireland, Nordics, and in USA. We have around 800 employees worldwide, and we provide solutions and services to help work smarter using the Autodesk AEC collections, our own tech called Navigate. ALTAIR is one of the global simulation providers. They've been been around for many, many years. They are headquartered in Troy, Michigan, in the States. They have around 300 or 3,000 employees worldwide, and they provide solutions and services within the simulation and analysis arena, where SimSolid is one of the products out of many hundred products. They do high performance computing, and also in the field of data analytics. So these are three main areas which ALTAIR is very active within. Now, just a little bit about SimSolid. SimSolid is not new. It's been around for many, many years. ALTAIR acquired the company, I think, several years ago, and they sort of recognized how this software is going to sort of have a huge impact in the FEA world. The main emphasis on that, it doesn't require any geometry simplification. So if you are doing anything in the FEA market, for example, simplification, creating elements, if in the structural world you have to specify beam elements, it doesn't require any of that, which requires work and effort, which means that you can spend more time working on the analysis, and it has the ability to work on very, very complex geometries and very, very large assemblies. And the other benefit of SimSolid is that it doesn't require a supercomputer. It's very, very fast how it operates, and you'll see that when we go through some of the examples. Now, so these are some images and a video, which is what we're going to talk about today around facades. And it just gives you what the software is capable of doing. You can see on the left-hand side, it's the geometry with the studs and all the complete geometries, the box sections, the slab. And on the right-hand side, you can see a video demonstrating the interactions between the several components. And you can see the text giving an idea how long it has taken to analyze that. So basically, it just demonstrates that you can actually work on your own geometries as they are, whether it's come from Revit or whether it's come from sort of a CAD geometry like Inventor. Now, this next slide is showing you a full, complete module of the facade. And basically, the idea here, you can see that you have the aluminium profiles as they are. They're not been simplified, the connections. So you can bring in complex, detailed geometry of your profiles as they are, with the brackets, the frames, the slabs, the facade structure, everything, and you can run it and apply some sort of wind load, pressure load, whatever you desire, and you can determine the deflections. Again, you can see this comprises of 23 parts, 2 different load cases, different materials. You can see there's no cleanup time. It works on the geometry as it is. Meshing time is a process of breaking the geometry down into different type of elements. The only time required is it's basically setup time, which is about 50 minutes, and it runs very, very fast. So you can do the whole process within 16 minutes and then repeat that if you have multiple design cases. Now this is showing you some sort of displacement results and stress results of the whole complete facade module. Now later on you'll see how more go through these examples, and you'll see how smooth and how fast it is working on your complete models, and you can go through the whole process very, very quickly. The whole idea is we will demonstrate going through the models live, so you can see how simple and how fast it is. In addition to that, we can actually customize contacts. So whether it's a bonded contact like a weld, or whether it's a sliding contact which is held by bolt connections. And this example here you see on the screen is 196 parts, and it was literally 4 seconds to solve. And if you have welded connections or bolted connections, you can bring them as they are. So just to sort of, I don't want to spend too much time on PowerPoint, so I want to spend more time on the actual SimSolid. Before I actually go through the SimSolid presentation, I was hoping to do a poll. So just give me a moment. So if I would, okay. So I would appreciate if you could sort of give me an indication of what you are currently using. Okay, just a couple more. Okay. Just gives an indication of how to be sort of emphasize as I go through the presentation. So just, okay. Okay, excellent. Thank you for that. So okay, so let's share the, so let me see when you can see it. You can see here, we have a mixed bag of the poll. So we have about 50% audience using some robot, which is a dedicated structure analysis software, which is no surprise there. And we got 20% people using ANSYS, which is a bit like SimSolid, and then other tools in there. So we got a mixed bag here. So thank you very much for sharing. I'm just going to hide that. Okay. So let's. Okay, so these are two examples. I'm going to demonstrate how SimSolid can be used. One is some sort of a framework structure. So typically, most of you probably use something like Robot, STAR, or dedicated structure analysis software. You will simplify your structure with line analysis or beam elements as more specifically, and then you'll do a separate analysis of both the connections. And the one on the right-hand side is a facade done in Revit. So it's been exported from Revit as a step file or a SAT file. And then we'll work on that geometry and we'll apply a wind load. And we'll have a look at the type of stresses and deformations we get in the structure. And then we'll have a look at something more relevant around facades when Mo goes through his applications. So I'm just gonna fire up SimSolid. I'm just gonna okay. Can you see my screen? Mo, do you want to tell me if you can see it?
Yeah, I can, yeah.
Thanks, Mo. Okay. So what we have here is the SimSolid interface. What you see on the screen is exactly what it is, no hidden buttons. And just to give you an idea, okay, these are, we can bring in CAD geometry from a whole host of different CAD softwares, whether it's a step file or a PowerSolid or ASYS or STL, including CATIA and also the Inventor software. So I have brought them in already. So what we have here is a structure with stiffening plates. Let me, you can see, and then we also have the complete bolted connections, including the washers and the nuts. So this geometry has been exported out of Revit. And you can see all the stiffened plates. Now what we can do in here is you can specify materials, and it's already, materials already been assigned, steel and glass, and you can see if it's already been assigned. If I sort of take it to one side here, steel's already been assigned, and you can customize the material properties to your standards. Now the other thing here is, which is very time consuming in traditional softwares, is the connections. So what we're going to do here is in the connections button here, you have an automatic connections button, and you can sort of, if you have components which are not connected to one another, have gaps between them, you can increase the gaps. I'm simply going to, now before I do that, I'm going to show you something else. So I'm going to cancel that for a moment. And I'm going to, all these stiffening plates, all these angled sections are actually welded. They're not, so we're not going to create connections. So I'm going to show you something else in here. I'm just going to isolate, not that one. So I'm going to isolate that one. And everything you see in there is going to be welded. So what we can do here, I'm just going to go in there. We can create, and what we can do here is we can specify a weld size. So we're going to go 5 in there. Let's make that 25. And we can do a group weld. And what it'll do now is it will go and create welded connections between every single member. You can see here, welded connections. And if I zoom out here, and let's show you here how many connections it's created. And you'll see there are many, many welded connections, almost 300 or over 350. Now what we're going to do here is, I'm going to reverse that. Now, some of these are actually welded, you can see here. So it was just a matter of reversing the selection. And we can do the same thing here again. And we'll just draw a window around. Okay, I'm just going to do a group weld. Same thing. You can change the weld size if you prefer. And you can see here, everything is, there you go. Okay, now you see that the bolts have been also welded. That is not what I had hoped for. So what we're going to do here is, I'm just going to go up to down here. So what we'll do here is, I'm just going to delete them. I'm just going to do this very quickly again. Because if you make a mistake, it's pretty quick, easy to sort of redo it again. That's how fast it is. And let's have a look. Oops. Right, that was that one. What I should do here, because I did a reverse and include the bolt, so what I'm going to do here is, I'm going to pick them from here. So pick everything O, that one, and that one we'll isolate. Now you see there, we have no bolts in there. So let's see that. And let's have a look. Zoom in here, you can see there. So the bolts are not there. So everything is now connected with the welder structure. And now what we can do here is, I want to show you what has happened to the bolts. So if I zoom into one of these bolts here, and I right-hand click on that. Okay, oh, I need to create the connections first. So let's go in here. Now, because I've created the welders already, I'm going to say do not create connections where there's welds. So if I pick that button there, it says connect on the unwelded parts. And now if I pick the bolt again, you can see what the red part demonstrates or illustrates that it is bonded. So the bolt thread is bonded with the bolt, and the bolt shank, which goes to the place, is got like a yellow color, and that's illustrating it's basically going to be sliding. So what I'm trying to emphasize here is that you don't have to modify the contacts. It comes in, the software recognizes, if you can see here on my browser geometry, the shape and size of it will illustrate it's a nut, bolt, or a washer. And SimSolid will recognize all that. So now we have all the connections. The only thing we need to modify here is basically, if I look at that plate where the bolt connections are, and show you the contact, it's by default a bonded contact. So in the real world, it's going to be a separating contact. So we can change that very easily by picking the I-beam. Let's go and pick the top plate here. And let's go on the other side as well. And then if I spin it around, pick that plate, pick the I-beam, and then go further up. There you go. We have 4 bonded connections. But I want to illustrate the fact that the bolts are strong enough, or the bolts can be fine. So I'm going to simply highlight all 4 of them. and edit. And this is how you modify contacts very, very quickly. We can have sliding without friction, or we can make it separating. And you can specify friction as well. Okay, so the boundary conditions have now all been set. So now what we need to do here is we can have a look at this. There is the separating contacts I created. And now what we can do here is set up the boundary conditions. So we're going to bolt these plates at the bottom. So what we'll do here is we'll fix it here and fix it here. And in this example here, we're simply going to apply a dead load. We're going to just look at the effects of gravity just to see what happens. So we'll define gravity in the Z direction. By default, it picks the Y. And now we're going to go and specify in the -1 direction. Okay, so what we're going to do here is, so gravity's been defined, the constraint's been defined, and everything's been defined. So what we're going to do here is we can simply run the analysis. If I press run here, okay, it's telling me, it's a warning that you are using nonlinear contacts. So you need to set up to take the nonlinear contacts into consideration. And that's something very simple to do here. You can click on setup here and you can have separating contacts, and then you can also do nonlinear materials and very large deformations for people who need to do that. And now we can press run here. So what it's doing basically is going through a convergence process. It goes through about 3 passes to find out if the results have sort of converged or unacceptable. And I'm still running it on a laptop, and it's pretty fast. And now it's going through the nonlinear contact phase. And then you can see how fast. Now, obviously, when you're using something like a dedicated software like Robot or STAAD, you would have to ignore the stiffening plates because it's these here. Okay, so now it's done. So what we're going to do here is what can we get from there? We can look at displacement results, and we can have the animation in as well. Obviously, it doesn't move by that much. You can see that it's not deforming by much. You can have a look at stress results as well, and you can look at the probes. It's down here, maximum. It's on the welded connections. And what you can also do here is, which is pretty cool in my opinion, is that it gives you a table of all your bolted connection with the shear forces and bending moment values in here. Okay, so this is basically a quick intro on how the software sort of works around the software. I don't want to spend too much time on it, but let me show you an example which is more relevant for you guys here. Now, I'm just gonna, if I look at the assembly here or the setup time, you can see this analysis. Where's it gone? Not on that one. Result. That's what I was looking for. You can see here it gives you how fast it runs. Total time there was 20 seconds. Now the other one example here, which I'm going to show you here, is the whole complete facade. And I've done this already, so it's got made out of glass and steel framework. And if I look at assembly information, it gives you an idea how many components there are, 421 parts in total. I have done the analysis already, because if I show you the results in here, this, can you see it only literally take 10 seconds to run. And the type of results in here you get there is, let's have a look, displacements. This displacement is across the whole facade. And if I press animation, you can see it. a wind load has been applied on it as a pressure. And you can see, and you can also change the deformations if you desire it. There you go. So this allows you to see what is happening to the geometry. Now, what I can also do here, which you probably see with Mo's example as well in a moment, is you can create bookmarks in here. So I don't want to see it. So if I click on glass stress, you can see there, this does not include the frameworks. It's purely glass. And you can let the stresses in there. And then if you look at the frame stresses, you can see here, same thing again, but now looking at the frameworks. And you can change the values of these. That's set to 10. If I make that one 5, and then you can see, and you can zoom in here. And then also one thing I forgot to mention, which I'm sure Mo will go through as well, very briefly, you can look at reactions on the fixed sides, between the connections, between the components, and it gives you forces and moments across the whole. You can see that wherever that framework there is fixed, it's been fixed all the way around. So it gives you an idea of what software is capable of doing. And before we go back, just got one more small poll before we go to Mo's presentation. So just bear with me. So okay. The next poll is basically, let me know when you can see it. Yeah, thank you, Mo. So I would appreciate if you take part in the voting process. Just gives an idea. Okay, just a little bit more. Okay, well, thank you for that. Let me share this with you. So we got about 45% that requires some sort of documentation or simulation for the clients. This is at the tender stage, and 55% no. And again, thank you very much. So I'm just gonna, right, Mo, you ready? Yes. You're good to go, Mo? Yeah,
okay,
good to go.
Great.
I'll mute myself now.
Yeah, thank you. Right, so I'm not going to introduce myself again, but for people who joined probably just after we've done the introduction, my name is Mohammed and I look after the technical department at SOTECH. So I'm not going to do a great deal of sales pattern here, just literally give you a very brief introduction about SOTECH, what we are, what we do, and then jump straight into the SimSolid and the analysis. So Wassam, he kindly showed some sort of frame analysis as well as some curtain wall. I'm going to show a bit of range screen cladding analysis, and feel free to ask any questions. I know so far there's no questions, but feel free. I don't mind if it's in the middle of the presentation. If you guys got any questions as we go, please feel free to share them. So SOTECH started in 1982 as a metal fabricator, and then I think we've got into range screen cladding around about 1998. In 2006 and 2007, we started actually fire testing, which was quite an advanced thing from SOTECH. You know, back in the day, obviously, no one's had a major concern about fire, but SOTECH, started testing the systems, the Optima range systems, fire testing them back in 2006 and 2007. 2008 we've had expansion. 2018 we've brought a full automated line and introduced that. And 2020 we've bought an office in London. which is in the centre. It's actually the building is located where there is quite a lot of architecture in there. It's called Building Centre in London. So you know, there's Powder Coating Company there, you know, rain screen manufacturer Kenwall. We've got the likes of Hill T, you know, who provides the subframe and subgrid, you know, all in that same building. So it's quite a you know, a good location. 2022, we started obviously looking at marketing outside the UK. So we are having some. We've focused on the Europe and Middle East, and you know, we are looking at doing jobs overseas. So not just focus in the UK. So obviously, our ultimate mission is to provide safe and sustainable facade solution. Now, in doing that, we always bear in mind manufacturability, which is quite important. You know, a lot of time you get involved with the job at the tender stage, and you know, you see a very nice kind of drawing, architectural drawing, but you know, the question is how are you going to actually make this? How are you going to manufacture? You know, it's easy to draw something which looks very nice, but in terms of actually, you know, making something safe and sustainable, and you know, to be able to manufacture, that's really the, you know, the core of what we do, what we offer. So pride ourselves in being one team, safe hands, integrity, and also go above and beyond where we can for our clients. So yes, that is it for in terms of the presentation. So I'm gonna jump into this SimSolid, which I've got two open, so I think it's this one that we want to have a look. So and that one, actually, that's the one that I've done already. So let's have a look at that one there. Okay, so Wassam, can you see my screen? Can you see the SimSolid screen? Yeah.
Yes, we can.
Okay, that's great. So I'm gonna look at this panel, which is a panel we've done for a job called Discovery Key a few years back. Now, why I chose this one, it's because it's a little bit, I wouldn't say tricky, but it's not your standard everyday rain screen panel you would do, like a, you know, like a square. So it's made from two triangular panels, kind of attached with a chevron going all the way through. You know, I've got a midpoint support here. I've got the rails in. Typically, we don't do calcs on the rails, so this is down to our whoever provides the subgrid. So you know, they tend to do the static calcs for us. So, but I've got it in there just so I can have something to hold the panel kind of in place. And then this is actually quite detailed. So what I'm going to be doing is, you might wonder obviously why I've got these as squares. So these, first of all, I'm going to apply a suction wind load onto this, so a suction pressure, and then I'm going to use these little squares later on to run another analysis and show maybe some abseiling, because you know, that's what people ask, you know, quite a lot. Now, all our systems are CWCT tested. However, the challenge nowadays is, and it's probably going to get even more with the golden thread, is that, okay, so we've got a CWCT test. Your test doesn't specifically cover a certain panel size, so what do we do? And this is where we get asked, okay, so can you do an you know, analysis to say that, you know, this panel is safe? You know, the CWCT test, it's there as a generic thing, you know, nowadays, and I would say probably every job we do, you know, there's some involvement in terms of simulation. There's always something that obviously our clients, you know, would like to feel safe and, you know, see it's actually performing, you know, in terms of the stability and performance. So this is what we offer this. You know, before, from my experience, I think we decided to go down the SimSolid route in quite a while back, in 2018/2019. Now, before that, I was actually trained by Wassam myself back in 2014, I believe 2014. Yeah, Wassam, he trained me in using Nastran. So when using Nastran, before Nastran, I used to use ANSYS a lot, quite heavily, and I'm going to obviously show you how you know, how good this is, but honestly, where we used to use Nastran or where we used to use ANSYS, one FEA could take us easily, 2 weeks to complete, and this is including report and everything. The amount of time you had to go there and play with the mesh settings and rerun, and every time you just wanted the mesh apart, you had to wait like 2-3 hours. This is SimSolid. When we first saw SimSolid, we thought that's a game changer. So hopefully you get the same feeling as I got years ago. And I'm going to be honest with you, years ago when SimSolid came out, we had it. It wasn't as good as it is now. It's had a lot of development, and which is a good thing, especially through ourselves, because we went direct to ALTAIR, and we've been talking directly to their development guys, and they've actually listened to us in terms of running analysis on sheet metal, like thin sheet metal parts. So it's really good, and it's changed, and it's a lot better now. So like you said, hopefully you're going to like what you're going to see. So yeah, so this is the rain screen panel. It's made from aluminium. So first thing I'm going to do is I'm going to assign some material to this. So if in my assembly, if I'm selecting the part, obviously it highlights here. So I've got my rails. I'm going to select all the rails, and I'm going to assign. So I've got my own library of materials, so you can do the same. So we've got specific material here. So for example, rails are 6063 extruded aluminium. So I select that. You can see the highlights there. So I've got my Optima hooks. So I'm going to select all the Optima hooks, and I'm going to assign the material to that. It's a 3103, typically grade aluminium. And then I've got the panel and rest of the parts here, which I'm going to assign the same material, 3103 to that one. So if you expand that, you can see that selected them too. So that's fine. Now the next thing we need to do is obviously to set the contacts. So we've got the material, so we've got the connection. And then I'm going to just use automatic connections. You can set the gap, so I'm going to leave that as 1 mil, and you can set the penetration, which I'm going to leave as 1 mil. What you could do is, if you've got a bigger gap and you need a contact, so i.e. if I've got something like that, which is a 5 mil gap in here, due to expansion, I could set that gap to be 5.5, so I'll pick that one up as well. But if I just run it without that, I'll show you the difference. So that's going to set my contacts. Obviously this model is quite heavy, and even behind here there's this part which I'm going to show later on. So it's going to take maybe a bit longer than what it did for Watson. But also I'm using I do have a supercomputer at work, which is a desktop, but this laptop I'm using today is quite old, so bear with me please. So I've got all my contacts here. These are all bonded, so I'm going to select them all, and I'm going to show you what this does. So on the first one, where the hooks are fully engaged, you can see it's actually picked the connection there, which is fine. On this one, which I mentioned, it hasn't picked the connection. Now, I don't really need this, but if you need this, what you could do is in this automatic connection, if I put this 5.5 gap, if I click OK, I'll kind of redo the contacts for me, and you'll see it'll hopefully pick that one up as well. Again, just depends on what you need. So let's do that. Yeah, I mean, again, depends on how realistic you want this to be. I mean, if this was in any other software, like Nastran or like ANSYS, you would have had to simplify this to its kind of bare bone, like literally, and you couldn't really run it as a solid anyway. You could have, you have to do mid surfaces. This would have been a nightmare. This would have been like half their work just to get the thing set up. Whereas now you just got the connection, you kind of click this, and then this kind of goes away and does its own thing. It takes minutes, literally take minutes. Now, Watson mentioned something which was the bolt and nut connection, which is very robust. But what you've got to bear in mind is, for a bolt connection to be recognized as a bolt, you need to have the head as a hex head. That's one thing that kind of drove me mad to find out, why, if I'm just got a simple pin there, why does it not recognize it? It doesn't, as long, you know, you have to have a hex head so that it recognize that. I use something called pin, which I'm gonna show you what that is. So I don't tend to model bolts, nuts, and screws and stuff in my models. So I put the holes in, and then later on I'm going to use a rotating pin to fix them, which I'll show you how to do that. And then also what I'm going to show you is once the simulation is done, you can actually get the reaction forces from it. So if you've got a specified screw, or you've got to specify a specific type of rivet, you can see the reaction forces, you know, from this SimSolid, and then go and compare it to your technical document from your supplier, whoever you're going to buy the rivet or the screw from, and see kind of where you stand and what's your factor of safety. So we're going to let this run. It probably would have helped if I've turned off the other SimSolid in the background, but I want to keep it up because I'm going to show something else on that one. So what I'm going to do initially on this panel is I'm going to run the analysis based on stiffness. And when you run an analysis based on stiffness in SimSolid, that's basically to determine if you need things like a stiffness. It's not great to show stresses, so mainly it is around kind of a stiffness of the material. So I'm going to select all these contacts again, just to show obviously this has picked up that contact there. See the one with the gap, you see it's selected there, so it's recognized that, and it's also recognized this one, which you could have these as kind of separating and closing contacts. It'll do no harm, but I tend to just run this without them. So we've got a few options. We could go manually and look for these contacts and change them to whatever we need. So if I show you this, I'm going to scroll down here until I find that one contact. So let's just see where we are. Not that one. It typically tends to group them together. So once you get one around this location, the other one should appear. So there we go. So it's doing the rails. There we go. That's doing the side of the hooks. There we go. So that's the one. So that's bonded. So if I right click on that one, edit contact condition, you can change it. You can disable it. You can change it to separating and closing. And what that means is it can kind of come close to the actual midpoint support, but not go beyond it, if you know what I mean, which is something you need. Typically they don't come really close, you know, the displacement tends to be very low at this point. So I'm gonna disable that, but because I'm gonna disable them all, I'll just rerun this connection again and set that back to 1. And then actually this will make it a bit quicker. So I'm going to increase and actually normal, that's it, yes, and then that will go and put the connections on. That should take less time because obviously it's only looking for very, very local contacts. So there we go, that's done, all bonded. Show you again. There we go. All the contacts are needed. Jobs are good. So that's these contacts. And then if I go back to the connections, I've got this pin connection here, which I mentioned. So I'm going to go around. So because I've got stiffening plates around the edges of this panel here, I'm going to put this contact on. It's selected both faces. So apply that one, apply. Then at the bottom, I've got another plate. Apply that one, and I'm going to apply that one. So I've got my pin connection. So if I highlight them, I say that one, and that one, and that one, and that one. And if I just go edit, so I need to edit one at a time, which is fine. So just go edit. You see, you've got different options here. You've got sliding, bonded, rotating. I want to rotate it. So basically, that will fix the plate in rotation, but in the transition, it will leave it free, which is what I want. And then once I've got these contacts all set up and the material, the next thing I need to do is I need to go to my structural analysis. So I'm going to click on that. I'm going to run one based on the stiffness. So we're going to look at the stiffness of this panel here. And first things I typically do is to set my gravity. So that's first things first. So like Wassim said, it's typically in the Y. So you change it on the Z depending on the plane that you've actually modeled this part. I've got gravity going down, which is right. Next thing I want to do is to set a pressure. Now, I want to set a pressure because it's a suction. I want to set it on the front face, but coming out of the panel. So I'm going to select that surface, select that surface, and that surface. And now what I'm going to do is I'm going to use 2.4 kilopascal because that's the serviceability limited state, according to the CWCT. 3.6 kilopascals, obviously safety, but we're going to go 2.4. So it's a megapascal, so I'm going to go minus 0.0024 and then click OK. So there we go. So that's applied. So you see the arrows coming out of the panel, which is what I want. And then the last thing I'm going to do is I'm going to apply a immovable contact to these rails, and I'm not going to move. So typically these are the faces you're going to have the brackets mounted on these. So I'm going to select these areas here to fix the rails in place. And if I click OK, then show you. So that's got the yellow contacts. That's on that's immovable contact. Then I've got the pressure there as well. So now what I'm going to do is you can actually give these names, which I typically do. So I would say on this one, say 2.4 kilopascal. So I know what that is. And then I'm going to give this a run, see what happens. So there we go. I think we're going to give it a few minutes. Like I said, this in the old days would be at least a day work just to find out that something doesn't work. And this was my challenge back in the day, I remember. And SimSolid is really a lifesaver for us because the amount of FEAs we get asked to run, the amount of analysis and simulation we get asked to run, it's we couldn't really do without SimSolid. We couldn't go back to anything else, purely just because of the time constraint. So there we go. Already got my results. So click on results, and then if I've got the displacement, and then there we go. So you can see the displacement here, and you can see it's actually right because looking at this midpoint support, it's closer to this face. So yeah, the deflection, the majority of the deflection is going to be around here, which is right because that's got a bigger span between the rails. So you can, with a bit of a common sense and just looking at the part, this is right what it's telling you. And if I click running this, just to see the animation, it's exaggerated. So yeah, it's not going to deflect that much. The maximum reflection point on this is 7.8 mil. So yeah, you wouldn't see it moving this much, but yeah, 7.8. And obviously this is, you've got to then you look at the CWCT recommendation, the L over 90. Measure between your fixings, divide that by 90, and see whether that's going to kind of satisfy the L over 90 rule from CWCT. Or if not, then you need to obviously have a look at the stiffness. So in that case, it's fine. But if that wasn't fine, we were probably looking at an extra midpoint support there, or an extra chevron there, just running across here, or just a standard horizontal stiffener, whatever that would work best. Now, if I stop the video and we look at the stresses, so the stresses, you see the stresses that's it's shown here. Because we've run it based on a stiffness, I don't quite agree with this. So this is where you need to kind of go and change this to adapt for stress and run it for stress, because I'm expecting the stress to be mainly around these areas on the hooks where this is kind of it's all over the place. It's been scattered. So I've already ran an analysis based on the adapt for stress. So if I just click on it, again with 2.4 kilopascal, So we're looking at the stresses here. So if it's I'm going to just change the numbers on here so the color changes so you can see. So that's better. That's what I'm expecting to see. And then again, based on that, depending on how high the stresses is, typically what we do, we're then looking at decreasing the centers or span between the fixings, or introduce, like we said, an additional, rail if possible. But this is the kind of thing I'm expecting, and you can see it's a lot smoother in compared to the end result. Now, I've also ran another couple of analysis just applying a point load on what I've called it like a bit of an upsale. So again, this is showing the stress, and this is showing the displacement of it. Again, seems right to me. Another one down here. Again, that seems all right to me. And if I look at the stress, you see the stress is going right on here, which is, again, that's right. That's what I'm expecting to see, the stress on this fixing here. So all good. I've got a few bookmarks, so I've already got them saved. There we go. Stresses, again, stresses, deflection. So that's that. I'm gonna show you something else because I mentioned about the pins. So this is the first analysis where I've applied wind load. So what we're going to show you is I'm going to go to this and then connection, and then I've got the rotating pin. So I've selected that one there. So we've got zoom on there. So there we go. So we've got two, and I'm going to just typically what I do is I decide on the worst one. So the highest one in this case is 89. So that's next to nothing. That'll be fine. And then I should show you one more. I think it's going to be that one there. Let's have a look. That one there, and that's 136, 82. So 136 the worst magnitude. Again, that's next to nothing. So a rivet or any type of a screw or any type of rivet would be fine in here. The pull-out load is next to nothing there. So and that's that. But yeah, you can have your bolt connection here, or you can use what I use. It's up to you. For me, it's faster just to select the pin and then kind of looking at the reaction of the pin itself. Any questions? Was there any questions so far?
No, so I'm just gonna do one more poll because we're gonna be tight for time. So let me change my screen. Just give me a minute. Okay, let me know when you can see this last poll.
Yeah, I can see that.
Yeah, if you could just see if you can, guys, just. Okay, thank you. Just a couple more.
Do you want me to?
Okay. Yeah.
Yourself, yeah, so you can show that.
Yeah. Just give me a minute. Okay, I'm just going to share this now, just to give you an idea of. So we've got a mixed bag here. So we get about, some people do physical testing, some use third-party consultants, and some use actual simulation. And let me know if you can see.
Physical testing, it's quite a good thing to do. However, you're limited to the rig you've got. You're limited to the size of panels you can test, or whether it's glazing or rain screen panel. Again, there's a lot of limitation, and it's expensive, and it takes a long time. So what we do, I'm not saying no physical testing at all, because we test our systems all the time. So do a test, but these tests are generic, and then maybe run a simulation and compare at least your deflection, your displacement in the simulation software to what you've actually got on the probes on the physical test during the physical test. I see what you can really. That's how I, through experience and through these, being involved in testing, that's how I validate kind of my own, simulations. So yeah, like I said, there's a lot of value in physical testing, but I think, you know, during this time where, you know, there's consultant on every single job that we do, and there's loads of questions, I think it's going to be impossible to physical test because every project's different. Every project, every panel size, every, you know, glazing size is going to be, you know, slightly different or a bit bespoke, especially when it comes to fencing cladding. Again, glass tends to be more generic, whereas aluminium cladding tends to be just anything that anyone fancies, really. So trying to do a physical test per project, I think it's just not going to be cost effective. And this is why I'm looking at this.
Thanks for that, Mo. So just wanted to share with everybody the case study, which there's 2 links here. We will send you the links. So this is 2 links. One goes to to Mo's company, and the one goes to our Symmetry web page. So both are exactly the same. There's a video there on the SOTECH page where you can have a look at the building as well. Okay, thank you very much, guys. Thank you for your time. Bye for now. Have a good day.
Thank you. Bye. Bye. Thanks.